Okay, getting another stream going. Been putting this one off long enough today. Can start off the stream with some very well-placed cat. I think this is currently one of his favorite boxes in the shop. Just hanging out, as cats do. So, this week I've had a bit of a diversion from the usual glitching project to do some prep work for kind of a class that my coworkers are working on. But now I'm back to the glitching, and I also happen to be at kind of an in-between point in that project where I'm switching from the kind of test harness that I built around an evaluation kit, switching from that to a programmable logic controller device that uses the same chip. And so I've done some work on this device already, a lot of it on camera, but not necessarily on the internet yet. It's been stuff that is still pretty far from being an actual edited together video, and it's stuff that I hadn't streamed it at the time because I didn't really have my setup to the point where it is now, but now it's easy to stream. So that brings us to the current mess on my desk. All right. So I've already had this open, obviously, but this is the device that I'm going to be looking at next. So this is, mounts on a DIN rail, like a sort of industrial kind of rack, and it's basically an industrial Arduino. It's got an LCD and a keypad there, slot for an SD card. Let's actually be recording this. So it's just the empty enclosure here. And got the protector still on the screen. It's got this little door for an SD card. Oh, let's not be... Hey, Tukes may be coming over here. So this has a very weird enclosure. Like, there's this door for the SD card, which is one of the main ways you can load programs onto this, but you need, it's kind of hard to open without a tool of some sort. And then this is just like a plastic piece that houses a circuit board, which I've also taken out, that has an SD card slot. So yeah, the SD card would usually go in there. So yeah, so that's the exterior. Let's unpack the guts from this experiment I'd put away before. Ground myself, put enough work into this particular device that an ESD-related incident would be pretty unfortunate. Oh, seems like Tuco might be coming back to join. Maybe I can go bring the camera. Probably better with the cable when I don't step on it. Hey, Jake, where are you? Well, he's going to be doing cat things. Oh, he dropped it way over there. And the camera's out of focus. I hear you, Tuco, but you dropped it too far away. Phil in chat is mentioning that Siemens positions this not as a PLC, but as a programmable relay, like a much simplified PLC, and that as far as they remember, it doesn't have any external I.O.s or extension I.O.s. Well, I'm definitely no expert in the marketing for this device. This one seems pretty capable. Like, it has Ethernet. It has, what is this? It has a built-in, like a small set of I.O.s built in. It has 4 relays. It has like 8 contact closures, and it does have some kind of extension bus. Like, they make basically I/O expanders that you can plug in on the side, And that's what this is for. That's one of the external interfaces that I have taken a look at, but it hasn't really been that fruitful so far. You can take a look at that on the circuit board. I think it's basically SPI in one direction and async serial in the other direction, and that they use that to address IOs in these expansion modules or like extra screens, or they have a handful of extension things. Let's see what else I got. There's the interior. Hey, Tuke, do you like anti-static bags? Good, you don't. Oh man, I'll bring him, or I'll fetch him, or I'll throw him a bolt if he brings one. So yeah, okay, so what is this? This is this was a experiment in trying to communicate with the add-on port. I think that little epoxy gubbins there is a, that's one of those dual inverter chips that I have in that SC70 package that I like to use. And I didn't feel like making a circuit board for this, so I just did it freehand. So, what is that? Or is that a transistor? No, some kind of chip that I use. I think that's, yeah, I think that's one of the inverters. I think I'm only... So power and ground are in the middle too. And so it looks like... I'm just not sure what's connecting to the bottom right pin there, unless it's on the other side. Oh yeah, this is strip board. Okay, that makes more sense. So this is like a breadboard. This is one of the Adafruit permaprotos. So that just being soldered to those two tracks means that they're connected over to this header and to that little wire. So I guess it's just two inverters in series to make this a non-inverting buffer. And then some kind of filter. Yeah, I think what I was trying to do was they have some kind of they had like a protocol where they were using a longer pulse duration as like an interpacket reset, and there wasn't an explicit chip select. So I think I was just using a little analog circuit to generate a chip select for the purposes of attempting to receive some data from it. But I think we can put this one aside. Tuco, what do you want, little cat? You're just climbing on me. Oh, he brought me a bolt this time. Okay. Alright, so that we can put aside for a bit. Now this is the internals of that whole PLC contraption with several things already modified about it. So, as you can see, this is kind of a weird shape that doesn't necessarily lend itself to, well, there's kind of a reason for having 3 separate circuit boards in here. So it makes sense to have really as much separation between the logic and control circuit board and the I/O circuit board as possible for safety reasons, and so that they can, they can release different versions of this with different I/O capabilities and still use the same processor board, presumably. So all of these I/Os, so these are the relays. Hey Tuco, that's a cat face. Over here, this is the power input, and these are 8 like switch contact inputs, and I think that one's unused. And so all of those are at this base level where there's kind of an I/O circuit board. Then there's another level up where you have Ethernet, and what is this one? I forget what that pin is for. There's this thing above it that's a place for grounding, but I think there's some kind of expansion connector there that wasn't present on this model, or that I removed to make room for something debugging related. I forget what actually goes there. Then that's the Ethernet RJ45. This is where you find kind of side modules that add additional I/O, but this connector itself is more like, low-level digital signals. And then this very top level is the actual LCD and buttons. And then there's this weird thing here. And so that structure is pretty much mirrored in what you see with the circuit boards. So it's also a weird stack where you have an I/O board on the bottom, and then a control board, which is the one I've been modifying the most, and then just a user interface board on the top. So, and then the SD card is actually on a little board that this is fixed to the drawer, so when you pop out the drawer, this board is coming entirely out, which is a little weird. And the SD card is usable for loading programs. I think you can also do firmware updates over the SD card, but part of the issue here is that we don't actually have, we haven't seen any evidence of a firmware update process out there in the wild, so one reason to try glitching it is to get access to the firmware in the first place. And then maybe we can learn more about how the update mechanisms work, if they indeed exist and aren't just totally locked down. So then this board, this is actually just separate things glued together. So there's an LCD module with its own flat flex here, and this is signal for the LCD module itself, plus it has power for the backlight. It has like a multicolor LED backlight. Then these buttons are normally separate, but I glued them on just to help make this more usable when it's taken apart. And they're pretty long since they have to stick through that plastic front bezel. And the buttons are all just routed through this little block connector here, this little header. So with that taken off, the next layer of this pie. And this is the one that I'm most interested in, so we'll come back to this. We'll save this for last. I'm just going to take it off for a second. We can look at what's underneath it. Oh, I see. It's a good comment in chat that pin that I wasn't identifying was probably also earth, and that the hole at the top was just for a screwdriver for releasing it, so that makes sense. I forget whether that wasn't present in this model or whether I had to yank off that connector, because I did, as you can see where that would have been, I put some SMA connectors on the board, which I don't think I'm going to actually end up needing. I think I'm going to end up putting my new glitch adapter on here, which doesn't need these, but since they're epoxied on, I'll just leave them where they are. This is a JTAG breakout that I added here. This was one of my, I guess this was my first attempt at doing a DIY flat flex. So I don't think well, I think I documented this process a little bit, but I still need to actually make a video about this. So that just breaks out the this footprint to JTAG. And on the bottom, you can see this is mostly the relays. They take up a lot of space. And then there is, so this is like a backup supercapacitor, I think. Yeah, it looks like 0.33 farad supercapacitor at 5.5 volts. So presumably that's providing like a backup supply for the clock. I haven't really reverse engineered this in detail. It looks like part of this is basically an I/O expander and part of it is a DC-DC converter. The input here is, I think nominally, I forget what the range is, but I know it's at least 12 volts. I think it also works on 24 volts. So it has a range of, I think it's something like 9 to 30 volts or thereabouts. So this is kind of the initial DC to DC converter. But then the other board doesn't just take like 5 volts. It takes, I think I measured like 8 volts going into that one. But it's got its own DC-DC converters. I briefly tried powering up the other board without this one attached. And I can power it just fine if I give it 8 volts on the right pin. And then it generates its own 3.3. But there's some hardware that the firmware looks for on here pretty early on. And so it ends up in a watchdog reset loop in the firmware, where it starts to boot and then it just resets. So something on here is necessary for the firmware to actually make a useful amount of progress. probably isn't too hard to replicate if I need to, but so far I've just been leaving this on and supplying power that way. So, yeah, okay, so not too much going on here. So, on the back side, we have a bunch of passives, parts of a switching power supply over here. I don't remember which one that was, but I suspect that was 8 volts down to... Yeah, there's only one switching power supply in here. These are just capacitors related to that supply also. I think it's going right from 8 volts down to 3.3. So a couple of modifications here. This one still has the Ethernet transformer, which I think I want to keep. I might have to remove it due to the underclocking that we did on the other board. I still don't know if the Ethernet transformer was interfering with the underclocking to the extent that I was actually able to do it anyway due to the limitations I found in the Ethernet PHY. So I suspect I can leave that on. I'm going to try that first and see if that gives me trouble. So over here, I did a bunch of crazy soldering on this side in order to separate the 3.3 volt plane from the board's 3.3 volts so that I could measure that. And so this resistor is bridging the board's 3.3 volt to this new separate 3.3 volt plane. That was kind of helpful initially. I don't know if I'm actually going to need that moving forward, since I turned out to be, there wasn't really much for me to do on the 3.3 volt rail. Everything I wanted was easier to see on the 1.8 volt V-core rail. So, I mean, I think mostly what I'm going to be doing here is kind of taking off this wire, ignoring a lot of this, and then taking the newer voltage glitching board that I built off of the eval kit and wiring it up to this one instead at the V-core rail. And I had this, which is mostly unused, but I was using this to break out some of the power rails. And I also need a trigger and a reset for the glitching experiments. And so I think I might have already broken those out on these 2 pins. I'm going to double check that, but reset was pretty easy. That's the same as any design using this processor. For the trigger, I had a technique worked out where I crafted an HTTP request I could send to this that, in combination with a particular PLC program loaded on here, I think in one HTTP request I can get it to both toggle a GPIO output and read something out of its flash file system. So I think I can use that as a synchronous time reference, but that's one of the big question marks to answer early in this experiment. This was that connector that leads... Let me get that actually in focus. This is the connector that leads to kind of side-by-side I/O expansion modules that kind of sit next to this one on the rack. And I didn't have a connector of the right pitch, and I didn't really want to damage that. So I ended up just like epoxying a larger header on there. It's like not the most sturdy thing, but it was enough. So, all right, I think the first thing is just to kind of get this set back up and make sure it works as I expect it to, and then start modifying it some more. Always got to have a baseline for these experiments. And it's kind of interesting to have the LCD and keypad attached, but it isn't actually necessary. It'll boot without both. It seems to have a write-only interface to the LCD. Doesn't seem to care about the keypad, and they manufacture a version of this that doesn't have the UI, so presumably it's pretty similar. It just doesn't have that last stack of boards. Phil mentions that the supercap is for storing the program state on power on, power off. That totally might be true also. This, I'm not super familiar with the non-volatile capabilities of this device. There's also some interesting memory. I forget which of these, but one of these is a MRAM, non-volatile magnetic RAM. So it has some way of storing the state of the program. So I think one of these is for the program itself and one is for the state. I don't remember off the top of my head which is which. But I tried tracing these on the logic analyzer, and there wasn't anything that looked like an easy way in. They didn't seem to have any settings that were otherwise sensitive. It just seemed to be like a copy of the program, the same as you'd find on the SD card. That might be a place to look again later if this doesn't prove interesting, but having a firmware dump will make investigating that way in certainly a lot easier. This board also had a lot of attention to separate grounding. So, you know, case ground, like Ethernet ground, definitely like very well separated from the rest of the system. And for testing purposes, I added this little bar here, but there's this whole, like this resistor here especially, and this safety cap on the other side were related to that earth grounding. Yeah, so I guess I did remove that earth grounding terminal. Yeah, that was like a big boxy wire terminal. That's what it was. They used like a 2x1 terminal block on the circuit board, but then only had a cutout for one of those in the plastic. So that's why I was able to get a bunch of free circuit board space for these SMA connectors. It's by taking off that whole 2x1 they were using. And then by repurposing that as a signal ground after actually bridging it like that. So a little bit weird, but seemed to do. All right, let's get this thing booted up. Well, I guess I can use the same 12 volts for my for my glitch injection power supply and for running this thing. Oh, that's totally not on camera. Oh yeah, and I don't think I've actually tried underclocking this rig yet. Well, I guess I must have. I already did the crystal mod. Yeah, so one of the leads on the left side here is a clock input after the onboard crystal's been removed. So, you know, I will have to give this thing a clock signal just so that I can talk to it even. I don't want to put too much stress on this connector. Okay, zoom out. So just in order to run this, I'm going to need a clock signal. Let's see if the function generator in my new scope goes up to 25 megahertz. If not, I will use the Chip Whisperer's function generator, or clock generator. Because my other signal generator only goes up to 10 megahertz. Okay. And the scope is still booting. Okay. So. Oh, copper tape. Actually, I think that was a little square of Pyrolux, since that's what I had handy. Let's see. Scope. That also maxes out at 10 megahertz, so I will use the Chip Whisperer, which is what I'm going to need to use eventually anyway. I will actually wire this up slightly different than I usually do because I don't want to underclock this yet. I want to start simple and add the underclocking after I already established that it's working. So, because I also want to make sure I get some footage of loading the program with the kind of GPIO pass-through into here, because I don't think I have that yet. And that'll be easier if I'm running it at regular speed, because I wouldn't have to go through my weird proxy server. All right, that said, just trying to keep tabs on which of these are ground and which of them are clock. Didn't put a ground right next to the clock, which is bad, but it'll be fine. I've actually got a lot of grounds that I broke out, so that should be all right. All right, that's back in place. Okay. Well, let's make a little room on here first by taking out some of the stuff that we're not using anymore. Because I need at least the clock generator off of this. So, soldering iron. Let's start yanking wires out of this thing. Okay. So these two wires were the power going from this to this board, which won't be necessary for this next experiment, but so I guess I can just take this off. Because now they both are just going to have their own 12-volt supplies, which is fine. This is the clock that it would normally be running off of, but it's been slowed down by a clock divider in this FPGA, and so I can't actually reach 25 megahertz with this, so for temporary testing I'll be using this clock instead. But not right now. I want to get this board off first. Let's see, I think this is the trigger, this is ground, and that's a knock on my door. I'll be right back. You know, this is actually relevant to the stream. I think this is a gift. Slight mailbag break. All right, some of these, some of those, lots of that. More of these. Yeah. This is a Heiko stand. That will be super handy. This goes with the soldering pencil that I was also recently gifted that should help out tons with the next super tiny wire job. Oh, very cool. Oh, well, thank you. I think this was from Kyle. I appreciate it quite a lot. Might end up helping with this very job. Whoa, I wonder why this one has a sponge instead of a brass thing. Or maybe it just has a space for the brass thing, but they also include a sponge in case you don't have one. I like the little brass things. I still don't know where the cat went. Yeah, they did send it in a pretty large box. Wow. Yeah, it's a lot like the other one, but it has this tiny cute little spot with a tiny cute little soldering iron. It's so little. Can we see the tip under the microscope here next to some everyday objects? And there's some parts, like a test point. There's an FPGA. So hold this left-handed. Oh man! Wow, you could like really get in there. And the actual iron itself is small enough that I don't feel like I'm going to kind of melt everything within the neighborhood. That's really nice. Cool. Looking forward to using that. Let's put this over here for now. Oops, and I'll just kick every light stand. Okay. So I think we're coming up on... Well, actually, I need to desolder this very fragile wire soon, but I think first I need to release that isopropyl alcohol. And I mean, it's not a huge tragedy if I cause some damage, because I don't think I necessarily need this board that much more in this experiment, but it would be nice not to break it since it's a useful thing to have around. Maybe I can get that under the microscope. Well, I'm going to need to for soldering in a sec, so I might as well make room. Oh, yeah. Microscope. Unintentional isopropanol glamour shot. Thanks, DSLR. Okay. That's a better view. How much soaking will it need? You can just kind of squish the glue and it starts to pop loose. Oh yeah, like a boss. That's what I'm talking about. Cool, now we can just apply some heat to those ground planes and that tiny little V-core pad. Oh yeah, Kyle mentions that they tried to use a micro soldering pencil on a TQFP and it didn't work because the pin was, or the iron tip was so small it just fit in between the pins. Yeah, that seems like it would do that. So this I don't really need finesse. I just need to heat these up so I don't damage the board too much. Great. Surviving the day for another mod. just need to unglue some more of this stuff. All the delicate stuff has been done. Lots of things to unglue. Doesn't come off quite as cleanly from the wood as it does from the circuit board usually. Still pretty good though. Oh yeah, that was on some Kapton that can come off too. Cool. Conversation about lab equipment and microscopes in the chat. There sure are some fancy microscopes out there. If you want to spend lots of money on a microscope, it's way possible. I've been pretty happy. Like, having a binocular scope if you're doing a bunch of work is super handy. And the one I got, I think, is still relatively cheap for binocular scopes. The brand was Amscope, like AM scope, and got it off of eBay a while ago for, I think it was something like $400. And it's nice because it's on like it has a weighted base, and then the microscope head is on a boom arm, so you can put it over the circuit board. It's pretty basic. I think the magnification is something like, on the low end, like 6 or 7x, and on the upper end, like 40 or 50, something like that. Which is fine. I usually end up using it on the lower magnifications for electronics anyway. Alright. So, this little glitch board has been working alright. It's been performing. So, we made this a bunch of streams ago. It basically exists to have a couple of these MOSFETs connected with a hopefully pretty low inductance path to the core of the microcontrollers, the core voltage of the microcontroller. And it has a little bit of capacitance that's always connected, and then a bunch more capacitance over here that's switched in when the glitch is not happening. So it kind of tries to turn off this MOSFET during the glitch as much as possible. And a lot of places to stick oscilloscope probes. This chip over here is another one of those tiny little dual Schmidt trigger buffers I like, and it's buffering the input. There's an SMA jack on the bottom. And then this also just happens to have a power supply, so it takes in, usually I've been using 12.5 volts because that's the max the MOSFET drivers can handle. And so that runs the MOSFET drivers directly. Then I also have a 7805 here to step it down to 5 volts. And then some 3.3 volt regulator from Microchip over here to step it down even further to 3.3. That's an MCP 1700, something like that. Some toasty tantalums that I harvested from another circuit board. They seem fine. So yeah, this is what we need to find some room for in the new device once we just verify that it's still working and put some useful firmware on it. Well, not firmware, but put a PLC program on it that we can use for a test harness. also got, oh, there we go. There's just a little bit of glue holding that down. And that's reset, which I also need to hold on to. So yeah, the device under test needs that trigger output, which is going to be one of those relays. I think I already went and cut the trace that went to one of the relays, because otherwise during the test it would just be clicking all the time. So it should be easy to see which I/O I was using for that. I'm sure I already broke out reset somewhere. So let's put this board aside. Tidy this up slightly. So, where does all this stuff want to be? Let's find out where vCore is so that I have some idea of where I can connect to this. Well, I'm getting a little ahead of myself by thinking about where to put this. I think first I'm just going to focus on that temporary connection that lets me plug the clock in for testing. So I think I am going to need a new jumper wire, and then I'll just kind of unplug this at the chip whisperer end and plug in another clock lead. I think I need my stash of jumper wires. I've got some that are already twisted together over there. Seems like Tuco's outside. Haven't seen him in a bit. Well, I do have a bunch of these long paired jumpers. I might just use those. These aren't twisted, but the wires will stay close together. So these are the clock output and ground. So I'm just going to make the purple clock and the blue ground, because that's what I've got. Ground and clock. Alright, so this FPGA is going to be idle for the moment. And that's fine. That's the reset output, which I'll set up soon, but not right now. Okay, I think, oh, that wasn't as on camera as I wanted it to be, but got that connected. Where the clock goes. Let's just keep all of this stuff out of the way. Can any of this stuff come off finally? Set that out of the way. And scrape off some of this hot glue. Oh, great idea, or great suggestion from Kyle for people setting up an electronics lab to try buying broken things. I agree. You can get stuff like that really cheap, and it's often a really good learning experience, and it's often also a source of equipment, although, you can't necessarily rely on that. Yeah, I used to do mail order surplus stores for like parts and stuff, but then sometimes I would get a chance to go to, there was this like store in Denver that I went to very occasionally that had gear that I usually couldn't afford anyway, but I would still get to look at it and I would buy weird parts from them. That's definitely how I learned like computers in general for the most part. I started out just borrowing my dad's computer whenever I could, but as soon as I could find people willing to just like give me broken computers, then I started going about it that way. Okay, so it's got 12 volts, clock, and for now let's not have anything else hooked up. So let's get that clock source running, make sure that it's running, and then apply power. So in this rig, the Raspberry Pi stuff over here is still turned off. Just want to attach the FPGA stuff to power right now. So let's this wire. It starts blinking. And I'll use that same Chip Whisperer VM we've been using. It's convenient to usually just run Chip Whisperer on the same machine. It saves me from having to copy stuff in and out of this VM all the time. Alright. So do we have the USB device on the bus? Not yet, but it's right there. Let's do that later. Okay. So I'm going to start out by just running, I'm going to run the script from our previous experiment just because I remember what's in there, and then we can do some diffs and maybe update the more recent script. But right now I just want a clock generator. Okay, so this is just set up kind of arbitrarily. Right now I'm making a 27 megahertz clock, which isn't what I want, but let's just get that on the scope. Ground, here's a ground, it's even a good ground. And gingerly attach this. Oh, that's on 20 volts per div. Let's crank that a little. It's not the best looking waveform. Okay, it's a little bit jittery, but it's probably within what I would expect from the clock generator. Let's get a frequency count on here. Oops, that's not what I want. Let's see. Yeah, 27.0. Okay, so now we should be able to switch it to 25, which is, so the reason this is on 27 is normally in this experiment it had been synthesizing a clock that's meant to be the same frequency, if not necessarily quite phase locked with, I mean it's trying to be phase locked. It's trying to generate a clock that matches the core clock in the CPU, but that clock isn't actually available externally, so that's why there's usually an FPGA dividing that down. But in this particular experiment, I want this to just replace the crystal that's usually there. So set that to 25, so that seems fine. And I think we can power this up. So power supply back at, let's use 12.5 volts, or even just 12 volts, just to be round. And that is currently just powering this, so there we go. Boots up. It is flashing at me. Is that a reboot loop? Or is it just waiting for me to set the time? What is this? Oh, I think this is normal. Okay, I think this is just what it normally does. I think the flashing might just be because the program isn't running or because there's an error or something like that. That's right. These things have a little weird user interface. This is like one of the debug pages that shows inputs, and these are outputs. I think these are counters or like some other kind of register that you can have in your program. And then here's, this is, oh, what is this? They're basically user-definable input buttons. There we go. But it's not just a matter of pushing this, you have to chord with escape, so escape and then left. Whoa, I pressed escape by itself and then that did something I didn't want. So that was a menu, which we'll look at soon. So I guess this is like the run mode where the program's normally executing. Let's zoom in a little bit and take the clock off. Did I reset it somehow? Okay, let's get a slightly better view. Okay, so if I give it a fresh power on. So that's running the program. So here's inputs, outputs, more state. Yeah, and then this is like a user input screen. So the left and right keys are still just going to navigate the menu, but escape plus one of those cursor keys is a programmable input as far as the PLC program is concerned. So I have a program running on there right now, which we'll take a look at in just a sec, which is just connecting the inputs to the outputs. Oops. It's kind of hard to do this with everything, just a stack of leaning circuit boards. So you can hear most of these click. Top one doesn't click. I cut the trace for the relay on that one because that's the one I've been using as a trigger, and I don't want it just clicking all the time because it would be annoying and it would just kill the relay. And of course I don't want to use the relay output as a trigger because then I would have the mechanical delay inherent in the relay contacts, which isn't going to be consistent. So then I think that other menu we were in, if you hold escape, I guess? Yeah. So this is where it starts up if it isn't auto-running the program or if there is no program in memory. So let's start this up and just reboot it because I want this in like factory default state. That's useful. Oh, is this something I need? Switch to OP. Oh no, that was a de-escalation of privilege. Oh, really? I think this is still set to the default password. But I hate entering it on this thing. Like, who's realistically going to set a secure password that they might ever have to enter on this? Usually you wouldn't. Usually you can do this over the network, but I could see getting locked out. Thanks, camera. Okay, so now I'm in admin mode again, fine. I was just gonna see if there's an easy way to wipe everything. I'm pretty sure there is. Maybe I just want this. So yeah, you can see that the SD card here is mainly just for making copies of the program that's usually stored on that internal memory chip. So now that I've cleared the program, I think if I start it now, it'll just come back into this menu by default. Yep, okay, so that's like what I'm used to as the default behavior. I forgot I'd already left this in a half configured state, already partway into the experiment. So now if I go to start, I think it'll give me an error. Yeah, empty program. So let's try the network interface while we have this running at regular speed. So that's the default IP. I've been using the default so far in my setup, so I don't have to worry about configuring these things. And luckily it doesn't overlap with any other networks that I usually have around here. Well, let's keep that on the screen for a sec and just get the laptop over here. Not make a mess. Fuss with my computer just a sec. Oh, I just noticed a question from the Twitch chat. BPAF asks, I wonder, what is that board you're holding? If that was the board, the like one that looked homemade, the like kind of coppery one, this one is a glitch adapter board that basically is a kind of a work-in-progress device that I attach to something that I want to extract firmware from so that I can inject power supply faults into it at a particular time. It's basically just like an H-bridge driver, but optimized to have really fast rise and fall times. Let's change this so that I can actually put the screen on the screen. Okay. So, in this particular configuration, the Ethernet should still be standard. I haven't modified the voltages, the transformer's still on there. It's clocked at 25 megahertz because I typed in 25. This Ethernet cable is probably too short unless I actually put the laptop on the desk, which is probably a good idea. temporary setup here. Oh, and if I forget whether I already mentioned it, but I might have just glossed over it because I thought it was clear from context, but these two use the same processor. So that's why I was using this as a stand-in. I was developing some confidence in a particular approach with a known device before trying it on an unknown device. And I know you can't see it because I covered it with copper foil for the new power plane, but and as you can see, it still works even after all that soldering, so that was nice. All right, so let's get this on the network, and then I will switch to the laptop, and we can take a look at that. Thunderbolt bridge. It's like not showing up as a network interface. There, it might help if I wasn't on the VPN. Ha ha ha. I mean, I don't know if that's why it wouldn't show up as a network interface, but I'm sure that doesn't help. Whoa. That's weird. I mean, considering the network wasn't working in the first place, it's weird that there would be an error. I've seen that in the past. I think it might just be a timeout, actually, for not having a link detected on the Ethernet after some time. I'm fairly certain this problem is on my computer's end. Oh, I might have to explicitly set this to something other than gigabit on this end. Let's get this on the screen. So that's the screen I want. Thunderbolt Ethernet. It's not getting a link here, so I don't actually want to set the IP address yet. Oh, fine. So let's just do 10 base T, because that's kind of what I want to communicate with at the moment. Full duplex, no flow control, regular size frames. Then let's give it an address like that. Put it on that subnet. I don't really want it to have a router, so I'm going to see if it lets me leave that blank. And don't really want IPv6 right now. So oh, great. Network restored, urgent event. Urgent, urgent, everything works. So, okay. So let's see if we can just ping this or, do other good networky things to this device. Pings are getting through. Oh, can I has web? And there's the web interface. So that's should be exactly what we're expecting here. I think this is still the default account too, or it might be something else that's not really any more secure. I don't think it's the default. I think it's just some other throwaway password. Okay. Cool. So that is the web interface. Logo system, variables. So I was excited about this at first because it looked like a way to kind of replicate the entire interface of the PLC over the web, which seemed like a useful kind of testing environment. But It was actually only really apparently useful for interacting with programs that were already on there. So the idea is you can build like a PLC program that displays a user interface, and then it'll work with this local thing, or you can use that same code on the web. But this doesn't actually, I had to check the manuals to verify this, but they don't let you control the built-in menus with this. But that's what led me to that idea about how to inject, how to send an HTTP post that would also give me or an HTTP request that would give me a page downloaded from the flash and a GPIO out. So that's why in the little program I had loaded earlier, which I'm going to reload in a sec. So that's why I have these buttons mapped from kind of the user menu keys to the GPIO from the user menu keys to the GPIO outputs, since these can actually be pressed over HTTP. So let's take a look at the HTTP going on here. Network. Pop this out. All right, so get a network trace. Lots of AJAX happening. Let's just go reload this. So a bunch of GIFs and scripts, and now it's polling. So I think these would have information from the screen or something. Yeah, so message ID -1, which is like nothing, I guess. How do I get out of this view? Oh, here we go. Neat. So if I press one of these buttons, we should start to see something new. Can I auto-scroll this? There we go. Well, I can manually auto-scroll it. Anyway, press a few of these. Man, this might be easier to see with something like TCP flow. Let's see if that actually is easier. Is that what I want? I think I just need to give this the right Ethernet interface. EN4 is what I'm working with today. Okay. There we go. So to show you what I've got running. So it's sudo tcp flow -i en4, and I'm using -c to just display stuff on the console, and then filtering it just to this host we're dealing with. So here's the polling. You should see if I reload this page. There's a bunch of stuff, and then some polling. Okay, here we go. So you can see that generated message click. Okay, so you can kind of get an idea of what's going on. There are these HTTP posts to /AJAX, and these polls are a message get. These buttons here, message click with another numeric code there, and it says OK in response. But they're all posts to /AJAX. So the first step of this train is to make a link between this AJAX HTTP post and some GPIOs. And then I found a trick where if you send these same parameters, but instead of in an HTTP post, you send them in an HTTP GET, it still has effect on the program. And so these keys will still cause GPIO actions, but it'll also read the contents of a web page from the file system. So that's where I'm headed next. But first we need to program the PLC to actually link these button actions with GPIOs. So for that, I've got a VM with their software that accomplishes this task. Let's get that up on the screen. First, need to make sure I can get this routed to the right part of the network. Do I want to NAT this? I think I just want to bridge with only the one particular network adapter. Let's see if I can get away with that. I forget which way I had to set it up last time. So bridge to Thunderbolt Ethernet. Let's see if we can ping the PLC from Windows now. Probably have to set the IP manually in here. I think the software for this does the network setup on its own, but I kind of want to do this manually just so that I'll have more information if and when it fails. So, man, I always forget how to do this in each individual version of Windows. Guess it's just this. Okay, I should be able to ping both the PLC and, general failure. What does that even mean? Can I ping the other computer? No, not even. No network access. Weird. Maybe I can get this through VMware's NAT. General failure. Whoa, where did that address even come from? 192.168.208.128? Oh, that must be VMware's NAT subnet. That's fine. Okay, so now if I ping 0.100, that should ping my VM host on an interface that is just between these two computers and the PLC. So that's cool. And I can ping the PLC itself. Great. So this software, let's open this from scratch too, just to have the footage of that. And let's hit the start button on yet another video recorder. Okay. So we're connected. We can also verify the connection to its website. Cool, all that stuff. All right, so now there's the actual software that you would usually use to program this stuff, which is oddly enough called Soft Comfort, which I guess means that it's more comfortable to program these on your computer than with the little buttons. I don't know. So it starts up like this. It kind of has like a schematic view for stuff that goes on in one PLC, and it has a mode for viewing an entire network's worth of stuff. So I think the way this works is I add a new device to this project, give it an IP address, which in this case would be the default, and this is the version I'm working with. Oh, I guess I've already got this. Oh, no, gateway. I don't want a gateway. Can I just leave that blank? These aren't actually on the internet. Okay. So now it's got a little model of this is my PC, this is what it sees attached. So I think we can already start interacting with this. Interesting. I don't know if that's real, because I wouldn't think it would go into run mode without having a program. Oh, it seems to be logging keys also. I wonder if I can see when I press a button. So you can also see they have these little short codes to identify most of the signals that you'll work with. So the prefix gives you kind of a hint about what kind of signal it is. These I's are digital inputs. C are the cursor keys, which are what I was sending over the network earlier. So I think the C should give me something that I can view that can be set either with some physical input or with a script. Oh, where were those? They were in this list somewhere. Those are like I/O expander pins too. Q's are outputs. Oh, there's the C. C. Oh, still trying to tell me about network errors. Let's clear all these errors. Okay, and then go back. The UI on here doesn't think the program's running. It still tells me I can start it. Yeah, empty program. So I'm just going to ignore. I don't think this is actually working like it thinks it is, but I don't really care. Anyway, I made a program earlier that just wires up inputs and outputs the way we want it. So that's this thing, C button to outputs.lnp. Come on, open. Alright, so that also has this logo device. And now if we scroll down the schematic here, get my head out of the way. So now you can see device up here, and then down here, it's just like it's sort of like an electrical schematic. You can have blocks that represent inputs and outputs. You can have blocks that have logic functions in them, or delay timers, or any of the other things that you might expect. I put all 4 of them in here for completeness, but we're going to focus on this path right here, leading from that up arrow to output 1, Q1 here. So I think here I think I need to download this plan to the device. Oh man, I forget whether it means it has upload and download. And I remember the first time I tried this, the directions were backwards from what I would have found intuitive. I think I want upload. Okay, no, I want download. Downloading puts code into the device. So I can change the mode. All right, now it's in run mode. So now this should be like it was earlier when I already had this partially set up. So running, got this little menu screen, and then this is the one where we can press escape and an arrow, and it gives me the click. So, all right, and I still don't really know how how synchronous these things are. What I seem to be the impression I've been getting so far from the timings that I have observed is that it's got kind of a relatively slow main loop that goes through iterations of kind of draining a queue of network stuff, handling all the UI stuff, handling all the program updates, and then setting outputs. And if it's the case that the GPIO and the network are really that synchronous with each other, then things are not going to be relatively easy. If not, then I have more challenges to figure out. All right. So I think we're done with this software for now. There might be some more. I mean, there's clearly a lot here that could be reverse engineered that might be interesting, but for now, this is all we need. I think the next thing is I actually had like a Python script for sending that cursor key to the device that we would expect to see triggering an output. So let's see if we can actually start using that as a trigger. Yeah, let's get rid of this VM for now. Okay, so this guy. Experiment for sending logged in commands to this logo device over HTTP. This did involve a little bit of reverse engineering because just in order for this to work at all, I had to make it through the kind of challenge response that was going on. So this does have to at least log in, which requires a password. And the crypto isn't great, but it's not really any worse than like HTTP basic or something. So let's see, we've got, oh, I can hear the relay tick right there. So which command was that? So in this case, the experiment, that was click 18. I forget which one click 18 is, but we can use this other experiment to tell us. So that was, hello? Do I need to restart this? Yeah. Okay, that's 18, the bottom one, which is still connected to a relay. That is 20. That's 24. And this one that I've made silent is 17. So, okay, we might want to keep that in our back pocket. So I'm going to make a copy of this that uses command 17, so we can verify that's silent. Oh, neat. That's interesting. You can actually see the up arrow flash on the LCD there. So if I run that script, flash. So in this case, this is also using that trick I mentioned. So in order to get a timing reference for a request that's also giving us a big chunk of memory, so we can try to glitch that memory read, this example here, so after it logs in, it's doing this thing that would normally be an HTTP post. So this command function is kind of emulating the HTTP post to /Ajax. So yeah, so it's doing a post with some data. Normally it goes to /Ajax and it just says OK when it's done. But the trick isn't in this function, it's in the override of the arguments. So by overriding and using this exact same procedure, except using it as a post on slash instead of a post on slash Ajax, then it still runs the command, but it returns this page that we might be able to use as a glitch target. So then I think the next step after this was I took this sort of proof of concept script and I turned it into a chip whisperer plugin. So that would be in here, targets. Previously, the chip whisperer experiments had been using this really simple HTTP plugin that I wrote, which just, the same way the simple serial plugin would trigger the experiment by sending a packet over serial and then, waiting for the trigger signal to come back. This does that, but over HTTP. So all this is really doing is using URLlib to send an HTTP request, and then formatting the results so that Chip Whisperer can summarize them. So building on that, this other script, this other Chip Whisperer plugin, logo HTTP trigger, this uses just basically some copy pastes from that other file. Oh geez, that's where Tuco is. Oh, that's so cute. I thought Tuco was outside this whole time. He's been, I don't know if I can even get the camera on him, but he's like between the window and the curtains. Super cute. I guess it's warm back there. All right, so this is the same thing, kind of cut and pasted. And this experiment is the same experiment we were trying on the command line before. You can see this one uses the quieter target, that's 17, which is the up arrow. And then that is integrated with the Chip Whisperer glitch explorer. So let's get the scope triggering again on the. So let's not quite get into the Chip Whisperer yet, since there's still a few things that we need to do. We need to actually attach the glitch board, which isn't physically attached yet. And I want to make sure that we can underclock this as much as I want to without introducing problems, because I don't think I've ever done this part of the experiment through the underclocked Ethernet proxy, so that's going to be new. But first, let's stay with the scripts. No. HTTP. So if we do that, we get that up arrow. So let's see what this looks like in the O-scope and start building around that. So I think I've already broken out what would have been going to the relay for that upper, the output that we were wiring up to that upper arrow, and therefore the HTTP request. PLC, destroyer of worlds. Yeah, basically. I mean, you hope these things are designed to have enough mechanical and electrical fail-safes. All right, so that was a piece of magnet wire that seemed like maybe what I'm looking for. It is currently sitting at 3.3 volts. Can I trigger on that? Maybe that is just 3.3 volts. Maybe it would be faster to look at the circuit board and just guess all the wires. Oh, I remember some of these. I put some headers where the Ethernet LEDs used to be to see if that would be useful for triggering the O-scope. And they are actually synchronous with Ethernet packets, but unfortunately those aren't synchronous with much else. Well, I don't know where this magnet wire goes, but my hunch is that it's reset, which explains why it's 3.3. Actually, I'm just going to try shorting it because I'm pretty sure this is reset. That'll tell me what's going on. I think maybe I had gotten to the point of cutting that trace, but maybe not breaking that out to a header yet. So let's take a look at that after I just test to see if this is reset. Oh, okay. Hidden magnet wire. There's actually two there. So I think one of those is reset and one of those is going to be GPIO. Let's try the other one. That one's at 0. And ooh, yeah, that one flicks when I turn this on. Let's get that on the screen. Look at that. Let's look at that at a slightly more useful timescale. .300 millisecond long pulse. Roughly. So a lot of this is going to be new because I didn't have this new oscilloscope last time I looked at this project. So one thing I wasn't really able to do before was just to throw everything I could get on one trace, including Ethernet and the power waveform. So that might be really interesting. I think I might save some of that until after we have more of this test setup wired, since I do want to get the glitch board on there. This is looking fine. Let's see about underclocking. I think that's the next step. So I think for that, yeah, let's power this off and do a little bit more rearranging in the setup, because I need to get the clock source from the other FPGA, and I should probably boot up the Raspberry Pi and make sure I can connect that. Well, we know this is trigger, so that can go to this yellow wire. Let's just test reset while we're here. Oh, here's a ground. Let's have an extra ground. Those are handy. There's already a ground through the power cable and through the clock cable, but this one was nice to ground these signals a little bit more, I don't know, to actually provide a good ground path between these two boards, I think, was my goal. This is reset. I think that's reset. I'm going to use the tweezers to verify. Tweezer time. Tweezers, so I think I can just short the collector and emitter on this transistor and we should see that reset. Yeah, can I do that repeatedly? It's hard to actually poke these. Oh, here we go. Yeah, that is definitely reset. Cool. So let's unplug the power. Is this Lappy going to sleep? Well, I think I mostly needed this Lappy for the Windows software, so let me put this aside for now. I think I copied those scripts to my other machine. If not, I'll do that soon. Ooh, these are making me nervous. Let's insulate that a little. tempting to use a zip tie for that, but I think that would end up just being annoying in the long run. Okay. So, clock change. This can unplug, and I can plug this clock carefully back into the ICE40 FPGA. I don't think that can even focus. Okay. Okay. Clock output. The ground and the 12 volts are just like right next to each other. And actually that's only the 8 volts, but still, that would not be a fun place to put the clock. Okay. Let's not worry about that yet. Just get the clock under control. So, back to the Mac. Okay, so this goes back to 27 megahertz, which is now reflective of our core frequency. Let's quickly check this out. Well, let's start the FPGA and then check the clocks out under the scope just to make sure they're sane. Where did I put that? Clock gen. Oh, right. Okay. Cool, so the FPGA is blinking now. You can see those LEDs kind of behind there. Oops. So, let's give this ground a better home. Okay, there's our 27 megahertz from the chip whisper, looking a little bit weird, but totally within our expectations. There's the output from the lattice. Ooh, weird. Look at all them harmonics. What does that look like at the other end? Well, it is the right frequency, and it's probably not so dirty that it's not going to work. Would be something to potentially look at if this doesn't work. So, now that this is underclocked, we need this Raspberry Pi contraption to talk to it. So Raspberry needs booting. Let's plug the Raspberry Pi into my shop network. So this is Ethernet and power. Alright. This this will tell us whether our underclocked Ethernet has a problem in the current configuration. This has not been tested before. So this side still has no Ethernet transformer, but this side does have the transformer, so it should still be AC coupled. May have gone overboard with the ferrite beads, but I was trying to get rid of the high frequency noise earlier. Okay, so let's go into Raspberry land. Okay. Well, now it's time to power this on and see if we get a link. So everybody's on that same underclocked 27 megahertz core frequency slash 5 point something or other megahertz external frequency. Starting. And without all my patches to disable auto negotiation, it's probably going to actually be kind of slow to get the Ethernet up, which is why I was trying to delay this part of the experiment as much as I could. That looks right. Let's see if we can communicate from the Raspberry side. Pings are good. Hey, Tuco. Oh, don't walk there, honey. Careful. Oh, how was your nap, Tiger? Don't be eating those. That's packing material. Okay. So, do I have any of those useful scripts on here? Probably not. I did proxy everything though, so I think I can run stuff remotely and it's alright. Did I copy those PLC related scripts into here? I wonder. I think I just need to SCP these. Oh, this has the... Oh, yeah, that's actually what I want. I just wanted this script. Command poster.py. This still has all the hard-coded bits that we want. I might have hard-coded the wrong IP address in there. There's no FIM. Sad face. Oh, this VM. Hey there, cat. Whoa, what a terrible default. Oh, sheesh, that color scheme. Fine. So, yeah, I'm just going to try changing this to the Raspberry Pi's address and see if I can just run this from inside the VM without any additional fuss. 'Cause that's kind of what I want. Where is a free terminal? I see you, boy. You're so little. I mean, he's actually kind of big for a cat. He just looks so little in frame right there. Okay, so I really don't trust MDNS enough to run my experiment through it. Look, it isn't even working right here. 10.0.0.184, why not? Okay. So if I put that IP address in here, just for testing, this will tell me if I can talk to this thing. I mean, the link being up is a good sign. It's probably working if it gets this far, but this will tell me to a higher degree of confidence. So we can ping the Raspberry Pi from here. Is this like a port number issue? Can I get to... Can I just curl this thing from the Raspberry? Oh, this might be time to start getting the Ethernet on the oscilloscope. Whoa. I don't know if that was visible. I just moved the cursor around on the screen and the display got all corrupted. So I think I might be unintentionally clock glitching this thing at the moment. I might end up having to change the underclock, which would also suck, but it wouldn't be the end of the world. Let's reset this. Link is down. Link is still down. Alright, link is still down. Okay, link just came up. Ooh, yeah. That's not a good sign. I would not expect the LCD to be unhappy with a lower frequency, so I doubt it's a communications issue. So... Oh, I might have been in error before, because I think I might have forgot to tell the Windows software to have this thing auto-start when you power it on, which could be useful. See if that command poster program runs now. Can I curl? I'm sending packets. Can I ping? I'm getting ping responses. Yeah, I'm getting pings. This is on the Raspberry Pi without the VM or the proxy in the picture. Although like HTTP proxy, it's still like doing the GDB thing. But this just wasn't giving me any traffic, or how far was it getting? Just some TX. Let's take a closer look at what's actually going on there. All right. Can I just... Oh, I feel like there are so many ways to go forward at this point, many things not working. That's interesting. But I kind of want to take a look at one of these PCAPs in Wireshark right now. What is today? I think it is one of all of today's traces. It's a little trace. Not much going on yet. Oh yeah, that's funny. And this is where we find out that it's something flashed to the LCD. That would be fun. That would be useful. Alright, this is part of a trace. So we've got some MDNS garbage from my computer, some pings. We could get an ARP response here. Can we filter by this MAC address? I wonder if this might be the TCP being too slow. I mean, it ends up sending the HTTP request and resending it? That seems fine. I wonder why curl isn't giving me the results. It's not that slow. Well, why was my proxy working? So, the proxy, I should be able to contact port 80 on the Raspberry Pi and have it act like port 80 on the PLC. I mean, I could also try underclocking it less, but it would be interesting to understand this problem. It doesn't seem like it's an Ethernet communication issue if pings work. The problems I would have before related to underclocking tended to be just the communication not working at all. It's flashing. Flashing 0. Well, oh, is it just really slow? Oh, or is it getting an HTTP okay and then never getting the response? Am I wedging the firmware somewhere in that part of the process? Interesting. Yeah, let's try less underclock. See if that helps. So, oh, how high can I safely get this? Let's have the scope monitoring the clock output just so I can make sure the PLL starts up properly. Because while, I'm underclocking the microcontroller, because of the way I have my clock divider set up, I think I might be using that intermediate PLL at a frequency higher than it might be happy at. With 27 megahertz core frequency, I think my intermediate frequency is like 150 megahertz in that Lattice FPGA. Alright. Delicate clock connection. Oops, there we go. Okay. It's 5.6 megahertz, normally 25 megahertz Ethernet clock. Can we make it to 40 megahertz? Guess so. Can we ping? Did any of that network stuff survive the clock frequency change? I think it did. So we could ping before. Can we ping now? I think the network didn't actually survive that. Let's reset that. Link is down. Urgent event. Go away, urgent event. Network restored. Urgently, network restored. Hi, cat. Okay, pings are working again. I hear you, Tuco. This seems similar. Alright. Let me try increasing that some more. Ooh, that's a 60 megahertz core clock. That's actually underclocked by exactly half. Well, let's reset the network interface. Link is down. Link is up. Oh, it finished this time. Man, it boggles the mind thinking about what kind of network programming on their end would cause an issue like this, where the HTTP request just never finishes if the processor is underclocked beyond a certain level. That's interesting. So that took 1.6 seconds. Let's see what else works. Like, do we have web? This is underclocked only by half, which is a lot better than 100% speed, but can we web? We're getting a lot of hex there. This is going to be really slow if it works. Probably even slower if it doesn't. Oh, we should probably try like a wget from outside the Raspberry Pi before jumping to a web browser. Whoa, IPv6, huh? That's probably fine. Oh, and it grabbed it. A lot of packets going through, but that's the right thing. So let's try a browser. Maybe let's try Safari just randomly. A lot of back and forth and then nothing. Interesting. So maybe it's failing to load one of the sub-resources this needs. Let's try Chrome with its network. Oh, there it goes. I guess it's maybe just failing occasionally, and so I have to retry to get some stuff in the cache. I mean, I just need to log in and press a button. That's what my experiment has to do. So it seems like this is, at this stage, it's working, but not very well. Let's see if we can run that command poker, or whatever I called it. Okay, this window, command poster. Oh, that's still on 192.168.01, which is not really what I want. I want this to route to the Raspberry Pi. Is it 144 or 114? 144. Okay. Let's try this. So I can ping this IP address, which is not really an indicator of much, because that just means I can ping the Raspberry Pi. But if I can grab HTTP from it, then that's actually being forwarded to the actual PLC. How's my network like here? Oh, am I still... No, this is still bridged. This VM is just on my shop network, so it should have access to the Raspberry Pi, and I was just pinging it. And I don't know if I have a key on here, but I should be able to try to SSH into it. Oops. That's right, I don't have the MDNS on here for some reason. So I'm not gonna have a password for that on me, but that's interesting. Was there maybe a reason for wget to be more successful? This is interesting. Interesting. I don't know if this is behaving differently because of the proxy or whether it's just borderline functionality the entire way. This is that same wget, but running from outside that VM. I mean, I guess it could just be at this borderline stage of functionality where sometimes it gets stuck at this stage. You know, I wonder if something's going on where there's like a loop of stuff it has to service at a particular rate, and underclocking it is causing it to never reach the lower priority items in that loop. And that would only make sense if there's some other time base involved in here besides the crystal oscillator that I'm replacing. But I think I might have to look to see if there's a 32 kilohertz clock that might be related. I think there is a 32 kilohertz clock, but it's internal, which is kind of the worst of both worlds for this particular case. Yeah, I might have to think about this some more and see if, get some more data to see what's actually causing this issue. Let's see if I can bump the clock rate up anymore, just to see if I can get past the borderline stage of this. This is underclocked by exactly half. Megahertz. Can I make it to 90 megahertz? That seems dodgy. And it looks dodgy. That's not treating my PLL very nicely. 80 seems to be kind of okay. Okay, so this is almost another 50%. Restart the network. Link is down. The link is down. Oh, the link is back. I also have not verified that the AC coupling is not an issue, although I think that wouldn't, that would be an issue that would affect even small packets, so that wouldn't, I don't see how that would contribute to any of these issues. Oh, I'm getting a wget. I just got one, and it was fine. I got another. Oh, and do I get another? This is the worst web server. It's just like, oh, I might give you a file eventually. can't imagine that the CPU, like if my hypothesis about the CPU running out of time for lower priority actions was right, then I wouldn't expect the CPU to be this loaded all the time. So this might also be some bad interaction with TCP timeouts. So that's why I might just need to, maybe step away from this for a sec, and the next time I look at this, take a closer look at the timestamps of packets in Wireshark and that kind of thing. I do think I at least want to get the Ethernet back on the O-scope, so we can take a look at that. I mean, I have to at least get some response from wget from inside the Chip Whisperer VM. Does this get more reliable if I reboot it? And the link comes back up. This is not so happy. Well, it just pings. So those timeouts, I think, are an artifact of my test setup. Hadn't chosen to spend the time to get to the bottom of that yet, and ruled it out in most of my experiments so far as a source of problems. But that could be worth getting into. How much of this? I mean, I just don't like how I can't get HTTP traffic through it all. That's a problem. And I mean, I could also be dealing with clock quality issues, because this is like way out of the spec of what the PLL is supposed to be dealing with right now in that middle FPGA. Well, okay, from inside the VM, can I make any progress? I have this program that should be able to make my trigger output tick. I think I want to change that address. It's not 144 now, right? Not 84. Let's reset this. Sometimes it gets hung in a way that is not apparent. Okay. Yeah, this is some interesting data. I think it might be time to think about this and plan some more experiments and take a closer look at the packet captures from this to see if that helps a bit. Logic analyzer pods ready. focus on Ethernet. Going to be treating the Ethernet as if it's a 3.3 volt logic signal, which for this setup is probably close enough. Oh, that one, this one. Okay, let's get that ARP ping back on, because that's something easy to analyze. And so it's mostly succeeding with the occasional timeout. So those are the outgoing ARP pings, the ARP requests. Oops. Oh, maybe this is related to the transformer, because that assumption of, I'd modified these both to be like DC coupled Ethernet, and that might be why I'm not seeing the responses here, because they're not, like if I plugged the scope in on the transmit side, I would probably see those. But right now they're probably not a voltage level that I can pick up with the current setup. Wow, this sounds like it's ticking. I wonder what that is. Well, it'll be interesting to take a look at the power waveforms on this. Oops, once I get that part hooked up. But I think I was excited to attach this board back onto the test setup, but I think I want to stall just a bit until I have more of a handle on exactly what it's doing right now. So I think the immediate next steps are mostly just to kind of stabilize this test setup a bit, find some clock rates that work out any problems with the underclocking or with the Ethernet proxy, so that I can actually trigger these experiments reliably. Once I get all that out of the way, then I basically just want to solder this on and start running some long experiments where I sweep through parameters and try to find firmware dumps out of this. On the previous experiment, it wasn't actually too hard to get a couple of species of glitch that gave me small dumps of clean chunks of firmware memory. So I was getting a 128K response, which included a clean 64K image, plus some other scattered bits and pieces of that same 64K region. So I think that's a stopping point for this stream. Yeah, the Ethernet has been very abused in this particular setup. Yeah, on this end, I've completely taken off the Ethernet transformer. I do actually have pins broken out for the transmit on this side, on the opposite side of the transformer, which could be useful. but I think I'm going to save that experiment for the next time and call it a day. Do we have any Tuco cam? Oh man, Tuco's been right here. I didn't even notice him. I was totally remiss on my cat camera duties, and he was right there. Can't trust a human to do a robot's job, I guess. Wow. Anyway, got a lot of good setup footage this time. Introduced the experiment on camera, which I don't think I'd actually done prior. So, I guess that's that. Thanks for joining this time. And yeah, there'll be more soon, more glitching. I'll be trying to work on some of the other projects this weekend. Finish up that little VFD thing and do some more work on the sort of longer term video projects like the kind of RFID reader Wacom tablet thing. So that'll be interesting. Tuco and I will be seeing you next time on the other side of the internet.